Hello. In this video, we introduce one of the most important and beautiful functions in mathematics, polynomials. Let's get started. So there's a lot of information on this slide, bear with me. The definition of a polynomial function is a function of degree n where all of your exponents, get this, are whole numbers. They can't be negative, they can't be fractions. They must be whole numbers. If there's one thing to highlight on your notes, it's that. Every single exponent must be a whole number. Now, for this polynomial function, typically we'll write it in one of two ways, okay? We'll either write it in what we call the expanded notation, where we've actually multiplied every factor together until we have separate individual terms. For example, you see here on the screen, in the middle of the page, f of x equals negative 4x cubed plus 5x squared minus 7x plus 3. All of those terms have been separated, expanded out, okay? That is the most common way you'll see in a polynomial functions equation written out for you. Formally, you see that at the beginning of the slide here, it's in descending order, meaning that your highest exponent comes first and your lowest exponent would technically be 0. So you continue bringing your powers of x down until you get to the 0 power. So you have a constant there, which is what you see in this example again. 3 would be a constant when your x has an exponent of 0. All right, so what makes these so beautiful and so powerful? Well, you're going to see a few examples on the notes today. But what I want you to notice first of all is that when we graph them, which is what we're going to try to work our way up to throughout this video by hand, and you can also use technology, of course. When you graph them, they are smooth and continuous everywhere, meaning there are no real sharp turns, like when we studied absolute value graphs. Remember that sharp turn? There are no sharp turns. As well, there are no gaps in the graph. Remember rational functions, how you could have a vertical asymptote where the graph completely breaks apart, or you could have a hole called a removable discontinuity? Well, that's not going to happen. So if you were trying to create a function that could model, let's say, a roller coaster's path, this would be a perfect function to use. Lots of different polynomial pieces put together. Maybe a piecewise function based on different polynomial parts, because it would be what we call continuous from negative infinity to infinity. There's no holes and there are no breaks in this graph. So that's one of the reasons they're so nice. They'll also be very nice when you get to calculus. They're going to be very, very nice for finding derivatives and integration. So that they're going to have a lot of applications for you. And they model all kinds of phenomena. If you throw a ball into the air and it comes down, projectile motion uses a polynomial function. All types of functions that you'll study in physics and calculus are in fact polynomials. So one of the things we're going to look at when we have an equation of a polynomial function, first of all, look at my example again in the middle. How do I know that this is truly a polynomial? Well, I would say this is a polynomial of degree 3 because its highest exponent when it's expanded in separate terms here is 3. I would also note that all of the exponents are whole numbers. 0, 1, 2, 3 are my exponents here. If any of them were fractions, like the 1/2 power, that would cease to be a polynomial. Think of that for a moment. If you have x to the 1/2, that's really the square root of x. And we know what that graph looks like. It's half of a parabola on its side, which while it's really cute, it's not continuous everywhere. It only starts at 0 and continues to the right forever. So that would be an example of a non-polynomial function. Similarly, what if you had a negative exponent, like x to the negative 1? Well, that would just be 1 over x, which is rational. That breaks apart at 0. So those, again, are examples of why we need to have whole numbers for our exponents. Okay, so I beat that horse. Let's get to our second cool fact about polynomials. By simply looking at the degree of your polynomial, which when it's in this expanded form, the degree is easy to see, like 3 in the example in the middle, we know how many potential x-intercepts there are. Real zeros of a function are what we also call x-intercepts. Why? Think about what it means to be an x-intercept. For a graph to have an x-intercept, that means that the path of that graph will touch the x-axis at that location. When x equals 3, for example, if that's an x-intercept, that means that the y value or the output of the function should be 0. In other words, 3 would zero out the function, right? That's why we call it a real 0. Now, an imaginary 0 still could be possible, but it would not represent an x-intercept. Has meaning. We'll talk about that as we continue in our series. So if I know that the degree of a polynomial is, let's say, n, it turns out that I could have up to that many real zeros. I could have potentially that many real zeros. Think about, for example, the parabola y equals x squared. What is the degree of that parabola? It's 2, so I could have up to 2 real zeros. I could have up to 2 x-intercepts. Now you might be thinking, Professor, you're wrong. The x-intercept there at the vertex is at 0. That's only one x-intercept, right? But what if I shifted that graph down a couple units, like y equals x squared minus 2? Well, now it's still degree 2, isn't it? But how many x-intercepts would I have? 2. So I could always have up to 2 x-intercepts if I have a degree 2 polynomial. Similarly, if I look at the example in the middle of the screen here, f of x equals negative 4x cubed plus 5x squared minus 7x plus 3. How many x-intercepts could I have, potentially? You're right, 3. At most 3 real zeros, also known as x-intercepts. One other fun fact, when we're trying to graph polynomials, they'll often have lots of turning points. For example, y equals x squared had one turn, right, at the vertex. But think about y equals x cubed. It also had one turn. But as you get into higher and higher powers, more turns are possible. So what we need to look at is the degree itself and subtract 1. N minus 1 will always be the potential maximum number that we could have for turning points. We could have up to. So in this example, where the degree is 3, how many turning points could I have potentially? 2, right? 1 less than n. Now, another cool thing that we're going to be using a lot in this video and the next is something called the factor theorem. You might even want to box this and star it and highlight it in your notes because this is going to come up again and again. The factor theorem says that basically if you have a factor of your polynomial, for example, x minus c, if that's a factor, then it must be the case that c is a 0 of that polynomial f. And if c is a 0, it works the other way. X minus c must be a factor. Now, that might seem very strange to you right now. What do I mean? Well, take a look with me at the example at the very bottom of the screen. It says f of x equals x squared plus 5x plus 6. Now, that's a degree 2 polynomial, which means it has up to 2 x-intercepts, right, and up to 1 turn. What else do we know? Well, this is one that we should know how to factor. What are the factors? Factors of 6, which add up to 5x when we FOIL. Would it be x plus 2 and x plus 3? Yeah, 3 times 2 is 6, and 2x plus 3x is 5x. Okay, those are 2 factors. Now, what if I asked you, I would like to find the x-intercepts of this function? Well, you would normally let y equal 0, wouldn't you? Because you want to zero out the function's y values. If you let y equal 0, though, we would use the zero product rule, which says something times something equaling 0 means one of those factors had to be 0 for the outcome to be 0. So if x plus 2 would equal 0, wouldn't x have to equal negative 2 if this is truly 0 here? Similarly, if x plus 3 turns out to be 0, x would have had to be negative 3. So I would say that my 2 x-intercepts for this function, this polynomial function, would have been negative 3 and negative 2. We usually write them small to large. All right, so that summarizes what we're trying to say in the factor theorem with this example. You saw that we had 2 factors, x plus 2, x plus 3, but that produced 2 x-intercepts, x equals negative 2, x equals negative 3, which is exactly what the factor theorem was trying to tell you. It was telling you that if you have a 0 called c, then you have a factor called x minus c. And if you have a factor, x minus c, then you have a 0 called c. All right, let's see if you can make sense of this with me in our next slide. So we have an example on this slide. It's f of x equals negative 4x cubed plus 5x squared minus 7x plus 3. Now, if I were to ask you how many real zeros I could have, hopefully you could say 3. And how many turns could I have? Up to 2. Great job. What we're going to talk about now, besides how many x-intercepts and how many turns, we're going to talk about what has to happen as we go toward the extreme x values of the function. So what I mean by that is we mentioned polynomials are beautiful in that they are continuous and smooth everywhere, to the left forever and to the right forever, to negative infinity to positive infinity. Okay, so what that means is we should have a pattern that we should be able to follow to smoothly sketch our polynomial graphs based on a couple of items. First item, the degree, right? The degree is going to tell us how many x-intercepts we could have, how many maximum number of turns we could have, but additionally, the degree will help us figure out what's happening at the extremes. Am I going to go upward in the extremes in both directions? How about downward? You can think of an equation right now that does that. How about y equals x squared, right? That one has degree 2, which is even, and it's going up in both directions as you go to the left and right forever. But what if I wrote y equals negative x squared? That's right, it would flip it down and they'd be going down in both directions. Now, what I just gave you was an example of the bottom half, the bottom row, if you will, of this box. It says that if your degree is even, which it is for y equals x squared, for example, and if your leading coefficient is positive, so both of those have to be correct, like y equals positive x squared. Degree is even, and it's a positive leading coefficient of 1. Then at the extremes, we should both be going up. And that should make sense. You're getting bigger and bigger, and they're staying positive because taking a number to an even power will always stay positive. But on the other hand, if we had an equation which had an even degree, like again, y equals x squared, but a negative leading coefficient, so again, another easy example, y equals negative x squared. Now you've taken the opposite of the output, haven't you? So instead of getting bigger and bigger, you're getting smaller and smaller. So we notice now that these two situations will happen if I have even degree function. But the example on the screen is an odd degree function. It has degree 3, okay? So what I want to show you is that when you have an odd degree function, you also can know what's going to happen at the ends, at the extremes. And we can see, for example, y equals x cubed for our first case. Think about that snake, right? The snake for y equals x cubed, didn't it look something like this? So it's increasing from left to right. So I guess it would be like this from the camera's perspective, right? So in that case, we can see that they're going in different directions, and that's because when you take a negative number to an odd power, it becomes more and more negative. But when you take a negative number to an even power, it would become more and more positive, right? So we can see that the negative and the positive will result in different directions here. So anytime we have an odd degree polynomial, we know that at the extremes, they must be heading in the opposite directions. But the question will become, are they increasing from left to right or decreasing from left to right? And you can see that based on the leading coefficient. In the first case, y equals x cubed, notice I was increasing from left to right because the leading coefficient was positive 1. On the other hand, if I had y equals negative x cubed, wouldn't that now flip the snake and it would look something like this? So now I would be decreasing from left to right. Okay, so one of these 4 possibilities will always hold. You might be thinking, really? What if I have a degree 16 polynomial? Will it really follow the same end behavior as a degree 2 polynomial? And the answer is yes. The degree getting bigger will affect, again, how many x-intercepts I could have and how many turns I could have. So you can see it turning around and around and around, but at the ends, if it's even, they're both going in the same direction, either up or down, based on the sign of the leading coefficient. So let's take a look at our example in more detail now. We have an odd degree polynomial because the degree is 3. So if it's odd degree, am I going in the same direction at the ends or different directions at the end? Different. Very good. So it's going to be one of these 2 scenarios, right? Then I have to ask myself, am I increasing from left to right or am I decreasing from left to right? How do I determine that? Based on the sign of the leading coefficient. What's my leading coefficient in this example? Yep, it would be the coefficient in front here associated with the highest degree term. That would be negative 4. Now, if it's a negative leading coefficient with an odd degree, am I increasing from left to right or am I decreasing from left to right? It would be decreasing from left to right. So you'd start off with a piece up here and then you'd end with the piece down there. Notice I leave a little gap here when I'm trying to visually describe the situation called the end behavior of this polynomial. So if you're just asked to describe it visually, which in this class, that's typically all I expect from you. If you do go on to study this in more higher level classes like pre-calculus and calculus itself, you would normally be expected to write it in this notation here. We call this limit notation. That would say in this case, as your x values with the arrow here, that means approach negative infinity, so negative infinity. That means as your x values go further and further to the left, get further and further, smaller and smaller, what's happening to your y values, your f of x outputs? They are going up forever, aren't they? So they're approaching infinity. And on the other hand, as your x values are approaching positive infinity, meaning as your x values go to the right forever or get bigger, what's happening to your outputs, your y value f of x? You can see it in the picture, they should be getting smaller. They're approaching negative infinity. And so you can see that is the case that I have described in these 2 cases. Okay. So you can actually click on the Desmos link provided if you have the electronic version of the notes in front of you, and it'll pull up this graph, and it should in fact have this type of end behavior. All I care about for your current class, the level that you're at, is that you can identify based on your degree and your leading coefficient sign which of these 4 outcomes to expect as you go to the extremes. The same direction or different directions, increasing or decreasing. Okay, once you know that, you're going to use that along with your x-intercepts to draw a picture. That's all we need. So let's head over to our next example and put this into practice. So here we have an example, f of x equals 5 parentheses x plus 2 times itself, in other words, x plus 2 squared, times x minus 3 in parentheses. Now, this looks a little different than we previously were writing our polynomials. Remember at the very beginning, you can go back and watch it if you like, of this video, I said that polynomial functions can be written in expanded form or factored form. This will be what we call factored form, okay? So factored form is very nice for graphing because if I'm in factored form, I can see my x-intercepts almost immediately. Really? Remember that factor theorem that I asked you to box or highlight at the beginning of the slide, of the videos? I said that if you have a factor, then you have a 0. And if it's a real number for your factor, it's a real 0 or an x-intercept. And so we see here, we actually know that we have 2 real zeros here. What are my real zeros? So if I was trying to draw this polynomial, what are my real zeros? Well, if x plus 2 is a factor, what 0 would be associated with that according to my factor theorem? It would be -2. Good job. So I could right now go to my graph, and at -2, I know there is a 0 there, or an x-intercept. I'll use another color in a moment. Similarly, because x minus 3 is a factor, what 0 or x-intercept is associated with that factor? Good job, it's +3. Now again, if you're wondering why is she switching the signs, I don't understand, think back to the factor theorem. You can go back and watch it again. Keep in mind, you're setting each factor equal to 0 and then solving, which means you end up moving the number to the other side, making its sign change. So +3 is another real 0 of this function. Now, one of the other things that you can do is you can find the degree of a function in factored form, but you have to be a little clever. Okay? We're always going to need to know the degree of our polynomial before we do anything with it. So if it was in expanded form, it was just the highest power, right? So some students will say, oh, the answer's 2. But that would not be correct because think about what's actually happening. X plus 2 times x plus 2 times x minus 3. You would do a lot of foiling there. And when you do x plus 2 times x plus 2, what's the highest power you end up with when you multiply x times x? X squared. And then if you end up multiplying by another x in the factor x minus 3, you end up with x cubed. In other words, the highest power for x will end up being 3. A shortcut, here you go. Add up the degrees of each factor. Add up the exponents of each factor. So in this case, 2 plus 1, or 3, is my degree. That's huge because the degree allows us to know how many x-intercepts we could potentially have. So I could have up to 3 x-intercepts. In this example, I only had 2. I wonder why that is. Well, didn't one of them get repeated? X plus 2, x plus 2, it's the same one, right? It turns out when it's repeated, the behavior there is very interesting. If you think back to y equals x squared, our basic parabola, at 0 was our x-intercept, right? Or we could say the factor was x minus 0. But it was being squared, and what happened? You got closer to it, you touched the graph on the x-axis, and then you turned around. It turns out that any time your factor has an even power, we're going to call that power the multiplicity, which really means how many times has it been repeated. This time it's been repeated twice. Anytime you have an even multiplicity like 2, which is what I'm saying in this fill in the blank here, if the multiplicity of your factor is even, the graph must simply touch and turn around because when you square it, or to the 4th, or to the 6th, or to the 8th, it's staying positive, so it can't dip below the axis, can it? So you're going to talk about touching the x-axis. You can say T for touch, or if you like B for bounce, you're going to touch and turn around, or you're going to bounce off of the x-axis at that location. So at -2, I'm expecting to touch and turn around. So I'm not going to actually cross the x-axis and change signs for my output. On the other hand, when I have an odd degree multiplicity, whether it be 1, 3, 5, 7, etc., anytime the multiplicity of a factor is odd for a polynomial function, the graph will in fact cross the x-axis there. So that makes sense if you think of y equals x cubed, right? At 0, because the multiplicity is odd, it's 3, we are crossing the x-axis and continuing on our way. So that would be, in this case, crosses for our fill in the blank. The graph will cross, I guess I don't need crosses, the graph will cross the x-axis. You could also say the graph would cut through the x-axis at that location. So at 3, I'm expecting to actually change signs, right? After 3, I'm going to go from either positive to negative or negative to positive outputs. All right, so the multiplicity of the first 0 was 2, which was even. And the multiplicity of the second 0 was 3, which was odd. So that meant that the behavior at each of those zeros was determined ahead of time. We knew that an even multiplicity factor meant that we're going to touch there, but an odd multiplicity meant we're going to cross there. So as far as graphing is concerned, let's go ahead and sketch our graph here with one more piece of information. We need end behavior to know what's happening at the extremes, right? And on our last slide, we talked about the degree being odd, telling us that at the extremes, were we going in the same direction or opposite directions? O for opposite, right? So they should be going in opposite directions at the ends, but how do I know if I'm increasing or decreasing from left to right? You can go back in your notes if you need to. That's right, look at the leading coefficient. What would our leading coefficient end up being for this problem? Well, because the coefficients were 1x and 1x inside the factors and a 5 in front, eventually we'll multiply 5 by your x to the highest power. So 5 is our leading coefficient, and it's positive, which would mean we should be increasing from left to right. Increasing from left to right. So let's draw our sketch then. That would mean this guy here goes this way, and at 3 it goes up. That would be increasing from left to right. Now what about at -2? Should I touch and turn around, or should I cross through the x-axis? Well, -2 had an even multiplicity, so we would touch and turn around. So we touch it, and we turn. Now one thing that's really useful is remembering how many turning points we could have. Because the degree was 3, we could have up to 2 turns. Notice I have 1 turn at the x-intercept itself because it was even multiplicity. But notice I'm going to have to turn around again somewhere because I have to get to 3, don't I, for an x-intercept. So where, we don't know. You'll learn in calculus exactly where that turn happens. And then we know that at 3, we're supposed to cross the x-axis, which is what we're going to do, and continue on our merry way because of the end behavior. So this would be what we call a normal sketch of this polynomial. If you wanted to show off, while you don't know, while you don't know where your second term will be exactly yet, you could find the y-intercept by simply letting x equal 0. Let x be 0 here, let x be 0 there, and then you know exactly what this location is if you want a really good sketch. But for a basic sketch, x-intercepts and end behavior is sufficient. All right, so this was a lot so far. Let's have you pause the video and try the next one on your own. Example 1 says, could you analyze the graph of this function? F of x equals -2, parentheses, x plus 3 to the second power times x minus 3 times x plus 1. Again, pause the video, see if you can work it out using your notes. Okay, remember, if it's in factored form, you know that a factor does in fact tell you a real 0, doesn't it? In this case, since the numbers are all real. So the real zeros would be -3 from the first factor, +3 from the second factor, and -1 from the third factor. If that's what you wrote, excellent job. Pat yourself on the back. All right. As far as multiplicities are concerned, we need to discuss the exponents, or how many times each factor has been repeated or multiplied. So I noticed that I have 2 copies of the first factor. So the multiplicity of that 0, -3 is 2, which is even. So what does that mean if I have an even multiplicity? Good, it touches and turns around there. What about for the 0, 3? 3, it looks like it's a multiplicity of 1 for that factor, and 1 is an odd number, which means what should happen at that location? Should I touch or cross? I would cross. Good job. Odd multiplicities, I cross. If you think you're going to forget, just remember the graphs of y equals x squared, where at 0, you touch and turn around, and that's even multiplicity, and y equals x cubed, where at the 0, you cross because of the odd multiplicity. All right, and finally, at -1, what happens? Its multiplicity, again, is 1, which is, in fact, odd. Now, when I add up those multiplicities, do you notice that I get the degree right away, which is helpful for me, especially if I'm going to graph? So the degree here would be 2 plus 1 plus 1, or 4, which is even. So that could potentially help me find the number of x-intercepts. There were up to 4. Here there were only 3 of them because one of them was repeated. It also helps me determine the number of turning points, up to 3 turns, and it helps me determine the end behavior, right? The end behavior is either going in the same direction or different directions at the extremes. If it's an even degree polynomial function, what should happen at the ends? Same direction. So it's either this situation where they're both increasing forever or this situation where they're both decreasing forever. So which of them would it be in this case? Well, I need to look at the leading coefficient. What is my leading coefficient in this example? Well, it turns out to just be -2 because, again, each of the coefficients of x was 1, so eventually it's just -2 in front. If it's a negative leading coefficient, I should be going down forever or decreasing my values for outputs at the extremes. So if you simply drew that little picture for me in your class, that would be sufficient. But if you do plan to go on to pre-calculus and calculus, challenge yourself to start writing this out in limit notation. As x approaches -infinity, comma, f of x approaches -infinity. And as x approaches positive infinity to the right forever, your f of x is still going down forever, so it approaches -infinity. Okay. Finally, the maximum number of turns, we've already mentioned it, was 3. Okay, so analyzing a graph of a polynomial is incredibly easy once you've practiced it and once you recognize you're in factored form. Let's head over to another example of this. Here we have f of x equals x squared minus 4x plus 4, a very nice, simple degree 2 polynomial. So if I wanted to graph this, I've just summarized the steps for us that we already know. We could definitely notice that we could factor here. Right now it's an expanded form, right? I can see the degree when it's an expanded form right away. What's the degree of this polynomial? Yeah, it's 2, which is even. We also can see that the leading coefficient is a positive 1. So what should be happening for my end behavior here? It should be going in the same direction and both increasing. So something like this should be happening. This one turns out to be a basic parabola, doesn't it? Degree 2 quadratic function. Remember, quadratic functions are special polynomials. Cubic functions are also special polynomials. Okay. As far as getting the zeros, though, factored form is helpful. So in this material, when you practice tonight, you're going to have a lot of them which could be factored easily, but as you move on throughout the course and in future classes, you'll have ones that are more complicated. So we'll need more tricks to find those factors. And we will get them, I promise, eventually. So if you wanted to get the real zeros here, we'd have to remember how to factor this nice quadratic. So we need factors of 4 with the same sign that when we add up the terms, we end up with -4x after foiling. Would it be x minus 2 and x minus 2? Because you multiply, you get positive 4, and you add -2x and -2x, you get -4x. Hey, is there another way to write that when you have something times itself? Yeah, you could take that something, x minus 2, and raise it to the power, the number of copies there are. In other words, the multiplicity, which is 2. Well, that's very helpful because once I have it in factored form, I can see a real zero. What is one of my real zeros, or x-intercepts? It must be 2. So the real zero in this case is when x equals 2, right? So I could go to my graph right now, and I could put positive 2 as an x-intercept. Okay, now that's great, it's a point, but that's not the end of the story, right? What is the multiplicity there? Should I be touching and turning around, or should I be crossing through the x-axis? Well, the multiplicity is the power of the factor, so its multiplicity is 2, which is even. So what do I expect to happen there? Touch and turn around or cross through the x-axis? I expect to touch and turn around. Okay, so now the only thing left to do for a very basic sketch, once you have your x-intercepts and your end behavior, we can draw the picture so far. So right now, if it's an end behavior where it's even and leading coefficient is positive, we said that in both cases, we should be increasing from left to right. So that means as we approach this x-intercept, something like this is happening, right? Can't see that well, so let me get another color for you. How about blue? Better? Yeah, okay. So as you approach the x-intercept, we should be going upwards forever in both directions. Notice that the x-intercept, we touched and we turned around at 2. So that one made sense. The only thing left to do if you really wanted to get a really good, high-quality sketch, not just a very simple sketch, we could find what we call the y-intercept, couldn't we? Because this is our y-axis. So on my test, I typically expect you to go a little further. To find a y-intercept, we simply let x equal 0. So in other words, find f of 0. Well, in this case, the easiest way to do that is when it's in expanded form, because that would mean that the first and the second term would go to 0, wouldn't they? When you take 0 squared minus 4 times 0, they're gone. You're left with just 4. You could have also done this using the factored form. 0 minus 2 is negative 2, and squaring it gives me positive 4. So now I know where to put my y-intercept. 1, 2, 3, 4. I'm going to get a better sketch this way. So at 0, 4 is my y-intercept. But note, I could continue the graph that way. Something like this is happening. Note that this is a parabola, so it has symmetry, meaning its axis of symmetry that cuts the graph in half goes through the vertex, which was at 2, 0. So that means at 2, 0, there was a line x equals 2 that cuts it in half, right? So if I went 2 units to the left here and I got to 4, that means if I went 2 units to the right, I get another location here at 4, 4. So I could definitely draw a better sketch by finding the y-intercept and then using symmetry if it's a nice symmetrical situation, which is what we have with a parabola. Also notice that the maximum number of turning points will keep you honest, because in this case the degree was 2. How many turning points could I have had potentially? Up to 1, which is what I saw right here, where I turn. So we've drawn a very, very basic polynomial. This is a quadratic parabola, right? But the idea remains the same. These steps are going to be consistent. You need end behavior, x-intercepts, y-intercept, and maybe some test points. So let's have you try this on your own in our next example with a more complicated situation. Suppose we have f of x equals 2x squared times x minus 2 times x plus 1. This is in factored form for you, so you already have a lot of information. Go ahead and pause the video and see if you can draw your picture yourself. So the first thing you did, I hope, was recognize potentially that you have 3 x-intercepts. Now maybe you only saw 2 of them, but keep in mind x squared is really x minus 0 squared, right? So x squared does in fact represent a 0 here of 0. So for my real zeros, I hope you found one of them is 0, that was from x squared. One of them is 2, that was from x minus 2, the factor, and one of them is negative 1. And you could write them in order like negative 1, 0, 2 to be more precise, okay? But on my graph, I'm going to show that right now. 0, negative 1, and positive 2. Now, we need to talk about what happens at those x-intercepts. Do I expect to touch and turn around, or do I expect to cross? Well, what was the multiplicity of 0? It came from x squared, whose multiplicity is 2. 2 is even, so what happens here? It touches. What about at 2? It came from the factor x minus 2. Multiplicity is 1, who is odd, which means I would cross there. And negative 1 came from the factor x plus 1, multiplicity 1, which is odd, so I would again cross there. So what happens? Well, I need to think about my degree now, because degree allows me to know how many x-intercepts there are, the maximum number of turning points, but it also will allow me to find my end behavior. So let's talk about degree. How did you find the degree again if it was in factored form? It's not just the highest power, that's expanded, right? But factored form, what did I need to do? I needed to add my multiplicities, didn't I? 2 plus 1 is 3, plus 1 is 4, so degree 4, or even degree. So I could have up to 4 x-intercepts. In this case, we had 3 x-intercepts because 1 was repeated, so we've covered them all. We could also have up to how many turns? Up to 3 turns, good job. Now to finish off the end behavior discussion, what else did I need to know? Because I know they're going in the same directions at the end. Yeah, I need to know the leading coefficient. What would it be? Positive 2 is correct, good job. So that would mean that at the extremes, they should both be going upward forever. So I can now superimpose that on my graph. At the most extreme x-intercepts, I should be going upward forever. So I go to 2, for example, and go upward forever. I go to negative 1, for example, and I go upward forever. Okay, we don't know everything about this graph, we're just doing a sketch. So that's the bare minimum right now. But at each of those x-intercepts, we know what's happening, right? We know that at negative 1, we said we are crossing the x-axis. So at negative 1, look what happens. I get closer and then I cross, because that was a cross. At 0, I'm going to touch and turn around. So I have to come back up somewhere. We're going to turn. We'll learn where in calculus. But I have to touch it and turn around. Touch it and turn around. And for 2, we're supposed to cross because its multiplicity was odd there. So that in calculus, you'll learn you'll turn somewhere. We don't know where. Ooh, make it continuous. And then we're going to cross through the x-axis. Now again, if you actually click on the Desmos link, you're going to see the accurate sketch of this graph. This is our meager interpretation of reality here, but the real graph would be best if you actually tested a lot more points and you had more accuracy, and that's what the Desmos link will provide, or a graphing calculator will provide. All we expect from our students at this level is a sketch. So do you have the right end behavior? Are you going in the right directions? Do you have the right x-intercepts or real zeros? And the behavior, are they touching or are they crossing at those x-intercepts on the x-axis? Okay, so again, look at your graph and make sure you kept yourself honest. How many turns could I have had if the degree was 4? 3 turns, and that's what I noticed. In calculus, you'll learn where those turns happen using something called derivatives, okay? So right now we see that it happened for sure 1 turn at the origin, but the other 2 turns we're going to learn about later on if we go on in math. Okay, so that's a basic sketch of a polynomial. I think there's one more question for us that's going to really make us think. Okay, so we're going to go in the reverse order. Here we go. It says, could we write an equation for a polynomial ourselves? Well, that's interesting. How do I write an equation of a polynomial? Well, a couple of ways. One, you could write it in expanded form, but the other one, which is what I'm going to recommend, is factored form. Factored form is really nice as long as you know the degree, maybe even the leading coefficient, but definitely if you know some of the real zeros or all of the real zeros, then you have your factors. So let's take a look at what they tell me in this example. They would like for the function to have a degree 3, which would mean if I have factors, their multiplicities should add up to 3. They also tell me that the real zeros that this function should have should be at -4, 0, and 2. What would that mean as far as factors go? So if I start my function, I have to name it. How about I call it f of x? You can call it p of x if you prefer, but some type of function notation here. Okay, that would mean that one of the factors, if -4 is a 0, one of the factors must be x plus 4. Well done. And if 0 is one of my zeros, no pun intended, what is one of my factors? Well, if you want to write it out kind of clunky, in a clunky way, you would say x minus 0, right? If c is a factor, if c is a 0, x minus c is a factor. But we'll fix that in a moment. And then finally, if 2 is a 0, x minus 2 is a factor. Okay, notice they didn't mention anything about the leading coefficient being positive or negative. So if they didn't tell us what's happening at the extremes, that's okay. You can keep it at 1. They haven't specified that. If you want to throw in -52, that's fine, unless they specify what they want the leading coefficient to be. That does make a difference. If you're wondering what does the leading coefficient do, it multiplies your outputs by that number. So it will make it 52 times as big if you put a 52 there. Okay, so keep that in mind. All right, so for a very basic setup, this is correct, but it looks a little bit tacky because x minus 0 could be just written as x, and we'll usually put that one in front. So x times x plus 4 times x minus 2. On my test, if I ask you to create a polynomial function based on the information provided like we did here, that's a great stopping place. You don't have to go further for me. In some of the homework websites, when you're practicing online though, they will, or in a textbook to be honest, they will expect you to know how to distribute. So let's just practice one of those right here. We could FOIL this out, and we would get x squared minus 2x plus 4x is positive 2x when we FOIL correctly, and 4 times -2 is -8. Then we still have this x in front, don't we? So what would we need to do with him? That's right, we'd have to distribute that x. So your final expanded version of the function, so not factored form, but expanded form, which is what a textbook or math software typically likes, would be x to the 3rd power, because x times x squared is x cubed, plus 2x to the 2nd power minus 8x. And then typing this into a graphing device, whether it's a calculator or Desmos.com, it's a really nice way to check that this function did in fact map onto this reality, where you have a degree 3, an odd degree function with real zeros or x-intercepts, -4, 0, and 2. So again, on my test, factored form is fine, but in most textbooks and in your e-practice websites, you're going to have pretty much always to factor it out, to FOIL it out, I should say. Okay, so we've done a lot in this video. We've talked about a basic definition of what a polynomial function is and all of the fun properties that they have, but it's now up to you to become a master of recognizing, analyzing, and graphing polynomial functions. So practice, because math is not a spectator sport. I'll see you next time.